In this very last lesson of the course, we will talk about how to implement a machine learning pipeline, albeit a very rudimentary one. Now, we will need to do so because we want to implement logistic regression. Now, logistic regression allows us to predict a binary, or in general categorized outcome, from a continuous input. So what are some examples where this might be useful? Well, for instance, if you want to predict gender from the height of a person. Now, even though gender might not be binary, it is still categorized. Or you can predict whether a student will pass or fail a test based on the number of hours that she studied. Again, a continuous input, number of hours studied, and a binary outcome, failed or passed. And another example would be to predict whether a client will make a purchase or not, which is binary, based on the amount of time spent on a specific website. Now, these are all examples where it would indeed be incredibly useful to predict a binary or categorized output based on an input that is continuous. And as I said, doing so will bring us to our first encounter with machine learning. So let's see how this is done. And the first step, of course, as always, is to generate our own datasets such that we can simulate different scenarios and get a better understanding. In this case, we need to generate a continuous X dataset and a corresponding binary Y dataset. So how do we do this? First of all, we generate X as being a continuous variable distributed according to a normal distribution. The mean will be 0 and the standard deviation will be 0.5. And thus we already have our continuous variable. But how do we now make a corresponding binary dataset that is nonetheless correlated with this X? Well, we can do so in the following way. First, we make a continuous Y, which is indeed linearly correlated. In this case, we make Y equal to a number times X plus B. And then this B is our noisy parameter. And this is just the formula for linear correlation between X and Y that we're now already very familiar with. However, this means that Y is continuous. So what we then do is we take this Y dataset, this intermediate dataset, and we binarize it. For instance, if this continuous Y is larger than a specific number, we just project it onto true, and if it's lower than a specific number, we project it onto false, or 1 and 0. And in this way, we have a continuous X and a binarized Y that is nonetheless correlated with this X. Now, to get a better feel of these datasets and how they are correlated with each other, we can visualize them. And that is what is done in this right plot. Here again, each dot represents a pair of values, X and Y. But we see that the X component of these dots can be continuous. It goes from -4 all the way to, let's say, 3.5. And X can have any value in between. However, we see on the Y-axis that the Y components of each dot can be either false or it can be true. And thus we clearly see that we have a continuous X value and a binarized Y value. Now, we see that they are correlated in the following way. We see that if X is very low, then we only have false values. Let's say X is -4 or -3, then we can be very confident that if we are given such an X, that the corresponding Y will be false. The same on the other side. If we have an X value between 2 and 3, then we're only here, and then we can confidently conclude that the corresponding Y value will be true. And in this way, they are correlated with each other. We can derive the Y value from the X value, or vice versa. If we're given a Y value, let's say true, then we can be confident that saying that the corresponding X could be between 2 and 3. However, these extremely low X values and these extremely large X values, they allow us to very easily predict whether the Y component will be true or false. If X is very large, it will be true, and if X is very low, it will be false. But of course, the interesting thing happens in between. Let's say that you have an X value of -1. Will you then predict that the Y value will be false, or will you predict that the Y value will be true? Because in our dataset, sometimes it is false and sometimes it is true. And this is, of course, the challenge of logistic regression. It's an algorithm that looks at our data that we're given and then makes a model that allows us to predict from an x value a corresponding y value, but of course also vice versa. So let's now look at the strategy to implement this logistic regression algorithm onto our data. And the first step already brings us to an extremely important part of any machine learning pipeline, which is test-train splitting. What you're doing here is you take your entire data set and you split it in a training part, which is roughly 80 or 85%, and a testing part, which is the remaining portion. So why split your data set? Well, the training part of your data set, which is the vast majority, you will use to actually train your model. And training a machine learning model means that you give it x values, and then for each x value, you tell it which y value corresponds to it. And in this way, you go through your entire data set, and for each pair of data points, you say this x value corresponds to this y value. And it is this relation for each data point that your model will use to actually learn a relation between these two data sets. Now, a concrete example that makes this training step very clear is the following. Let's say that you're training a model that should be able to distinguish between pictures of dogs and pictures of cats. Now, in the training step, what you do is you take the training data, so roughly 80% of your overall data set, and you tell the model, this is the picture of a dog, this is the picture of a cat, another cat, a dog, and so on for each image in your training data set. And then the hope is that because the model is shown so many pictures of dogs and so many pictures of cats, that it will be able to distinguish between the two if it is shown a new picture. So just remember that the training of your model happens on your training set, where in this case for logistic regression, you tell for each x value which y value is correct. So after training is done, you want of course to get an idea how well your model is performing. Is it any good or not? Well, to figure this out, you turn to your test dataset. Now remember, your test dataset is still a dataset of pairs of values. For each x value, there is a corresponding y value. In logistic regression, we have a continuous x value and a binary y value. And therefore, what you can do to check your model is to give it only the x values and let it make predictions on the x values in your test training set. Now, of course, the predictions that our model makes on our x values can be directly compared with the real y values that we have in our test data set. Now, because the model didn't have these x points in its training data set, it couldn't prepare for this test. And that is why testing our model in this way gives us a very good representation on whether our model is any good or not. But of course, testing is for after training. So let's take a step back. At this point, what you've done in the first step is to split your entire dataset into a training dataset and a testing dataset. The next step is to initialize the model. In this step, what you're going to do is you're going to tell Python, in this case, what model you want to use. In our specific case, we want to use a logistic regression. And then we give this object a number of parameters, which just specify which exact algorithm this model will use to train. Now, again, more details in the dedicated course on machine learning. Then once our model is initialized, we let it loose on our data. And this is the fit or the training step. In this step, we just give the model our data and we tell it to abstract patterns from our data. And this will oftentimes be the longest step and the heaviest step computational wise. But after however long you're waiting, at some point the model will be done training. And then of course comes the evaluation step, testing whether the model is good or not. And this is of course again where our testing dataset comes into play. Now, before we get into the details of how to test whether your model is any good or not, let's go to the code and see how we can actually make this model and let it train on our data. Now, the first thing that you might notice in this Jupyter notebook cell is that we have to import a lot more tools. Now, this is of course because machine learning is a bit more involved than just basic statistics in Python. In any case, the first step is to define some parameters. In this case, we define the slope, which we will use to generate our y dataset. We define the noise parameter, which also takes on the same role as before. and then the size of the data sets that we will generate. Now, what is important for machine learning algorithms is that this size is always large enough. Even 5,000 will be quite low, but it makes it such that the training will be much quicker. Now, in these two lines, we generate our two data sets. Remember, X will be continuous, just a distribution of random numbers distributed according to a normal distribution with a mean of 0 and a standard deviation of 1. Now, the corresponding Y variables need to be binary, so either 1 or 0, which are then mapped to true or false. Now, remember from the slides, what we do to generate this Y is we first make it linearly correlated with X. So just multiply it with a number, which is a slope times X, and then we add a random number, which is this B. However, here you see that we have some extra things in Python. We have this .reshape in X, and we have this x.ravel where we generate Y. Now, these things make it such that X is continuous and the corresponding Y is this binary function. If you go back to the slides, if we define these variables like this, then we will get variables that are visualized in this way. Now, the details again, I will leave for a corresponding video on the Code for Data Science YouTube channel. So now that we have our continuous X dataset and our binary Y dataset, which are nonetheless correlated to each other, we can go to the first step in our machine learning pipeline, which is to split our data into training and test sets. Now, to do this, there is this very useful function train test split of sklearn. This function returns 4 arrays, the X values for the training set and the Y values for the training set, but also the X values for the test set and the Y values for the test set. And to do this, we simply do train test split, we give our X dataset and Y dataset, and we give it a test size, which in this case is 0.2, which means that our test set is 20% of our dataset. And then correspondingly, our training set will be 80% of our complete dataset. Then remember, the second step is to initiate our model, which is what we do here. We give it a name, and then we initiate it with logistic regression, and we give it the parameters that determine the specific algorithm that we will use. Then once we have initialized our logistic regression model, we want to train it on our training dataset. And this is done very easily. So we have our model, we add .fit, and we give it our X training and our Y training. And running this step will actually train our model. So once you come at this point and you run this cell, it will probably take some time to train. But once it is finished, you will have a completely trained logistic regression model, which you can use to make predictions. Now, to make predictions, we can do the following. We take our model, which is now trained, and we do .decision function. Then we give it our X test, so the test part of our dataset that wasn't used during training, and we will get a Y score, which are the corresponding Y predictions for each value in this X dataset. So now that we have trained a model, let's now go back to the slides and see how we can test such a model. So how do we now evaluate whether our model is good or not? Well, as I said before, what we can do is we can use our model to make predictions on our X values of our test dataset. And then these Y values, these predicted Y values, can be compared with the actual Y values of our test dataset. Now, this comparison can be done in several different ways, specifically for logistic regression. And each way depends on the context in which you are using this model. So let's briefly go over them. The first tool to evaluate our model is the confusion matrix. And it can be visualized as follows and contains the following information. Because the variable that we are predicting, our Y variable, is binary, the confusion matrix in this case will be a 2x2 matrix. On the x-axis, we have the predicted label, either we predicted it to be true or false, and on the y-axis, we have the true label. So either our Y value is true or our Y value is false. So then combining these two axes, we can see the following. In this square right here, it shows the number of predictions that we predicted to be true and which the actual label was also true. So these are correct predictions, and we will call these true positives. However, it could also be the case that we predict an outcome to be true based on the corresponding X value, but in actuality, the real y value was false. And thus we made a wrong prediction. And this is correspondingly called a false positive, because we predicted it to be true, but it was actually false, and thus a wrong prediction. Now, on the other hand, we can predict a value to be false, and it is in actuality indeed false. So again, this is a good prediction. Now, this is a true negative, because we are right in predicting that the value will be false. But of course, we can also make a wrong prediction. We predict it to be false, but in actuality, it was a true label. And thus, we can use the confusion matrix to very quickly gauge the performance of our model. We want the highest numbers to be on this diagonal. When we predict something to be false and it is false, in this case 404 times, and we predict something to be true and it is indeed true, in this case 378 times. So let's go to the next performance metric. And this will be the ROC curve. But before we talk about this curve and how it relates to the performance of our model, let's talk about different performance metrics, which is very important to distinguish between the two and to know where to use which one. First, we have the accuracy. Now, the accuracy is just the number of correct predictions compared to the overall number of predictions. Let's say that you made 1000 predictions and you got 600 predictions correct. In this case, you have an accuracy of 60%. Another performance metric is the precision, and this measures the following. Of all the true predictions that you made, so each time you predicted an outcome to be true, how many of these are actually true? And this metric is called the precision of your model. And the last performance metric is called the recall. Now this answers the question, how many of the actual true values in our underlying dataset did we actually predict correctly? So let's say that in our true dataset, out of the 100 data points, 65 of them were actually true. However, our model only predicted 55 of them. In this case, the recall will be 55 divided by 65, or we recalled 55 out of all of the 65 true values. Now, to give you an idea of when to use which metric and how this is very important to judge your model performance, consider the following example. Let's say that you want to make a model that predicts a very rare but very deadly disease. Let's say this disease only occurs 1 in 10,000, but you really want to detect this 1 in 10,000. But of course, you don't want to have too many false detections, because you don't want to tell anyone that they have a very deadly disease. Now in this case, measuring the accuracy of your model is not such a good idea, because consider the simplest model that just says for each person that they don't have the disease. Then on average, you will be right in 9,999 cases of 10,000 cases. So this is an accuracy of 99.99%. So this is an incredible accuracy, but it fails to achieve the main objective, being able to detect this disease in this one person out of 10,000. So the accuracy here is a very wrong metric to look at. So let's then consider that you look at the recall. Let's say that you have a model that predicts that every person has this disease. In this case, you will of course predict that the one person out of 10,000 people has this deadly disease, and the recall will be exactly 1, because you detected every person that had this disease to indeed have this disease. However, you also told 9,999 other people that they have this disease, even though they don't have this disease. And thus also not exactly what we want, even though the recall is 1, the maximum. Now this specific model, telling everyone they have the disease, will of course have a very low precision, because out of the 10,000 people that you predicted had this disease, only 1 of them actually had this disease. And the precision says that of all the true predictions, in this case everyone, how many are actually true? So only 1 in 10,000, or 0.01%. So this model, telling everyone they have the disease, will have a very large recall, but a very low precision. So intuitively, it becomes clear that what we want in this specific case is to have a model with still a large recall, because we really want to detect this one person, but also a large precision, because we don't want to have to tell many people they have a deadly disease while they do not. And thus we see a trade-off between recall and precision. And this trade-off is exactly what the ROC curve looks at. It is the curve that is plotted with the false positive rate on the x-axis, so predicting someone to have the disease while they actually do not have the disease, and the true positive rate on the y-axis, so actually detecting someone to have the disease. And that's what we want, is to have this line as high as possible on the y-axis while being as low as possible on the x-axis. Because in this case, we have a high as possible positive rate, so a perfect prediction, but also a very low rate of false predictions. So actually we want this curve to rise rapidly here, and then naturally it will taper off right here. Now the area under this curve is a number for how rapidly this goes. Now we see that in this example, the area under the ROC curve is 0.87, and this indicates a good model. Now an alternative version, which even more closely relates to this trade-off between precision and recall, is the PR curve. And this is exactly what you think it does. On the x-axis it has the recall, and on the y-axis it has the precision. And also here, what you want to have your model to do is to maximize the area under this curve. Now, because we want to have an as large as possible recall, so we want to be as close as possible to 1 on the x-axis, but also as high as possible that we can. Because if this curve drops off too rapidly, then that means that we're getting indeed a large recall, but we are losing precision rapidly, and thus making too many false positives. So ideally, we want this to be just a straight line all the way up to here, but that is of course impossible. The area under this curve also goes between 0.5 and 1. Now, all of these visual methods and the corresponding metrics that allow you to evaluate the performance of your model are also implemented in the same Jupyter notebook cell as before. Now, I won't be going into detail into these plots right here, but of course you will be able to find this in the corresponding video in the Code for Data Science YouTube channel. And you can see that here we have all the figures that we looked at. Now this brings us to the end of this short introduction about machine learning concepts. Now machine learning is a vast subject with a large number of applications. And in fact, an entire course would still be too short of a time to cover all of it. However, in my upcoming course, Machine Learning for Data Scientists, we will go through the concepts of machine learning in the same sense that we did here for statistics for data scientists. So keep an eye out for when this course launches. And if you made it all the way up to this point and watched all of the lectures, then I am incredibly proud of you, because it has been quite a lot of material. Now, if you made it all the way to the end, I do indeed want to hear from you and to know what your thoughts are about this course. I want your feedback. So if you could do me a favor, then please leave a review and also mention that you indeed made it all the way to the end. So again, congratulations and best of luck in your data science endeavors.